Okay, let's dive right into this. If you've ever stared down a complex circuit board and just felt totally overwhelmed by that maze of wires, resistors, and power sources, well, you are in exactly the right place. Today in this explainer, we're going to unlock what are basically the ultimate cheat codes for understanding electronic circuits. I'm talking about Kirchhoff's circuit laws. And look, these aren't just dry, dusty academic rules. They're literally the fundamental principles that make our entire modern electrical world tick. Here's exactly how we're going to break it down today. First, we'll look at the brilliant Gustav Kirchhoff. Second, we'll review the circuit analysis toolkit. Third, the first law on the conservation of charge. Fourth, the second law on the conservation of energy. And fifth, we're going to solve a real circuit together. Section 1. The brilliant Gustav Kirchhoff and formulating the rules of electricity. Gustav Robert Kirchhoff was a German physicist born way back in 1824 in Prussia. His early research was laser-focused on electrical conduction, and that exact work led him to formulate the laws of closed electric circuits in 1845. Now pause and do the math there for a second. Born in 24, formulated the laws in 45, that means he completely revolutionized our understanding of electrical engineering when he was just 21 years old. Crazy, right? And as if that wasn't enough of a flex, he later became the absolute first person to verify that electrical impulses travel at the speed of light, while also making some massive leaps in the study of spectroscopy and blackbody radiation. Section 2. The Circuit Analysis Toolkit. Looking at two fundamental truths. Now, what's really interesting here is how perfectly these two primary tools contrast when you're calculating resistance and tracking current flow in complex networks. On one hand, you've got the first law, which deals strictly with current. You'll often hear this called the junction rule. On the other hand, you have the second law, dealing exclusively with voltage, widely known as the loop rule. And honestly, keeping these two domains completely distinct in your mind, that is the absolute secret sauce to mastering circuit analysis. Section 3. The first law, conservation of charge, or the rule of the node. Before we start throwing math around, we really need to define what a node actually is. Simply put, it's just a junction connecting two or more current-carrying routes. Think of it like a super busy traffic intersection where a bunch of different roads all converge. Cables, wires, electronic components, they all meet up at this single point. And here is the golden rule of that intersection. The total current entering a node is exactly equal to the charge leaving the node. I really want to emphasize this framing right here. Absolutely no charge is lost. Ever. It's a perfect system of conservation. To put it differently, if you take the algebraic sum of every single current entering and leaving that junction, it has to be perfectly null. 0. Now, to keep track of all this electrical traffic without totally losing our minds, physicists use a really straightforward standard sign convention. It's super simple. Any current entering the node gets a positive value. Any current exiting the node gets a negative value. And this brilliantly illustrates how those conventions actually play out in practice. Imagine you've got a node with 5 different wires connected to it. Currents 1, 2, and 3 are entering, so boom, they're written as positive I1, I2, and I3. Currents 4 and 5 are exiting, so they get written as negative I4 and negative I5. Because of the conservation of charge we just talked about, the math of this first law dictates that the algebraic sum, so I1 plus I2 plus I3 minus I4 minus I5, must perfectly balance out to equal 0. Section 4. The second law, conservation of energy, or the loop rule. So, leaving current behind for a minute, we are firmly stepping into the world of voltage, closed loops, and series circuits. Just like the first law told us no charge is lost at a node, the second law states that the algebraic sum of every voltage in a closed loop has to be equal to 0. Basically, in any closed network, if you track the voltage all the way around the entire loop, the sum of every single voltage drop you encounter is going to bring you right back to null. It's literally just pure conservation of energy in action. But there's a little catch when applying this loop rule, which is perfectly highlighted by this quote from our source. It says, "It is essential to maintain the direction either counterclockwise or clockwise. Otherwise, the final voltage value will not be 0. So the crucial point to take away here is that consistency is absolutely your best friend. You get to choose your path around the circuit, clockwise, counterclockwise, whatever. But once you pick a direction, you've got to stick to it for the entire loop, or your math is just going to fall apart completely. Section 5. Solving a real circuit and putting these laws to the test. All right, theory time is officially over.
Let's get hands-on and set up the parameters for our seemingly unsolvable circuit. We've got 3 resistors in this closed loop. Resistor 1 is 2 ohms, resistor 2 is 4 ohms, and resistor 3 is 6 ohms. Our primary mission as circuit analysts today? We need to determine the exact electric current flowing through this entire setup.
Let's move to our methodology and see how this all builds, step by step, to crack the problem. Step 1. We arbitrarily choose our current direction. Let's just go with clockwise. Step 2. As current flows across a resistor, there's a potential decrease, so our voltage drop, V equals IR, will be signed as negative. Step 3. We sign our EMF, or electromotive force sources. If the current moves from low to high voltage, it's positive because energy is charging at the source. If it moves from high to low, it's negative because energy is emptying. And finally, step 4. We substitute our values. So, following those rules and moving clockwise, we start constructing our equation based on Kirchhoff's second law. We hit our first resistor, so that's a negative IR1. Then we hit our first EMF source moving from low to high, so that's a charging, positive E1. Then 2 more resistors give us negative IR2 and negative IR3. Finally, we hit a second EMF source, but this time moving from high to low, meaning it's emptying energy, so it's a negative E2. And because it's a closed loop, the whole entire thing has to equal 0. Now we get to watch the math effortlessly condense down. We substitute our given resistor values of 2, 4, and 6 ohms, and we'll assume our EMF sources are 10 volts for E1 and 5 volts for E2, based on our source example. So our equation becomes negative 2i plus 10 minus 4i minus 6i minus 5 equals 0. Group those variables together, and it shrinks beautifully down to negative 12i plus 5 equals 0. From there, if we isolate I to find our current, meaning we move the 5 over to get negative 5 and then divide by negative 12, we arrive at our final electric current, 0.416 amperes. And hey, pay close attention to the sign here. The result is a positive number. In Kirchhoff's world, getting a positive result confirms that our initial guess to calculate the circuit clockwise was spot on. If it had been negative, it would just mean the current was actually flowing counterclockwise. See, the math always tells the truth. It's genuinely mind-blowing when you take a step back and look at it. I want to leave you with this final thought to ponder today. If a 21-year-old Gustav Kirchhoff hadn't figured out the fundamental rules of these closed electric loops way back in 1845, would our modern electronic world, from the smartphone sitting in your pocket right now to the massive power grids lighting up our cities, would any of it even exist? It really puts into perspective just how incredibly foundational these cheat codes truly are. Thanks so much for exploring the circuit with me today in this explainer, and definitely keep questioning how the world around you works.